The Autonomi Network recently pushed its v.6.7 update. Almost immediately, telemetry across the network registered a spike in data velocity. Looking at the latency chart for a standard 15 megabyte file payload, the baseline download time fell sharply, dropping from a 10-minute average to 2.5 minutes. At the same time, the payload hit a 100% download success rate across all updated nodes. This validation wasn't isolated to a small test lab. The run utilized more than 900 active, multi-region nodes spanning multiple providers. Optimizing a decentralized network is more complex than tuning a centralized server, where hardware and connections are strictly controlled. In this environment, every endpoint is an unmanaged variable. To understand the engineering behind this four-fold reduction in latency, we have to deconstruct the specific architectural splits, the routing adjustments, and the cryptographic logic fixes deployed in this update. Reliable, high-speed throughput requires surgically clearing bottlenecks at every layer of the stack. Brute force hardware upgrades are not an option. Up until this week, Autonomi operated under a significant architectural constraint. The client and node codebases were tightly conjoined. This meant that pushing even a minor improvement to the client forced a heavy, network-wide upgrade across every storage node simultaneously. The v.6.7 update physically separates the client layer from the node layer. Now, updates can bypass the nodes and deploy directly into the client. By decoupling the architecture, engineering teams can ship client-side bug fixes and feature improvements independently, moving at a much higher velocity. The primary focus for this new iteration cycle is an adaptive client, designed to automatically adjust upload concurrency on the fly. Instead of forcing users to experiment with arbitrary magic numbers or manual tuning, the client handles the configuration dynamically to ensure performance. Decoupling the architecture shifts the engineering burden away from complex node configurations and toward building scalable end-user products. While download latency dropped cleanly, achieving reliable upload velocity exposed a different failure state. Engineers identified a bug where files falling into very specific size ranges were failing to upload 100% of the time. A failure rate that consistent points away from random network congestion and toward a deterministic logic error in the code. The issue was found in the cryptography, specifically in the way the network uses Merkle trees to calculate and verify data chunks during an upload. Normally, a file is divided into chunks and hashed upward into a balanced, even-depth Merkle tree, allowing efficient verification. But if a file size required an odd-depth Merkle tree, the process stalled at the pool count calculation phase, rejecting the entire operation. The system's pool count calculations were functionally incompatible with the geometry of an odd-depth tree. The logic was corrected, and the patch landed alongside 5 strict regression tests. These tests act as a strict gatekeeping mechanism. They ensure this specific class of mathematical failure can never re-enter the codebase during future updates. In trustless storage, deterministic logic bugs must be eradicated before engineers can accurately diagnose true network layer performance issues. With the codebase stabilized, we can look at the network layer to see how that 10-minute download time was compressed to 2.5 minutes. The retrieval process starts with the Kademlia distributed hash table, the primary routing mechanism nodes use to discover one another. Maintaining routing table health requires nodes to query each other continuously, so they can agree on storage locations across a decentralized map. By tuning the Kademlia iteration process, engineers created tighter query paths. Nodes can now locate target data using significantly fewer multi-step jumps. But finding the data faster is only half the equation. Once those encrypted chunks arrive at the client, they carry a heavy cryptographic processing load. The system previously processed this encryption sequentially. The v.6.7 update shifted the mechanics to batch decryption. Processing these tasks in parallel generated a 3-fold increase in download speed on its own. Optimizing decentralized throughput requires a dual approach, minimizing routing distance across the network while reducing the processing load at the destination. While a logic bug in the code can be fixed permanently, unmanaged infrastructure produces unpredictable hardware variables. Tracking down these remaining environmental variables is the current focus for ensuring absolute reliability on large file uploads. The network relies on community nodes, which means the physical hardware configurations are unmonitored and highly variable. One persistent edge case disrupting uploads traces back to a very basic hardware discrepancy: misconfigured system clocks. When initiating an upload, a client sends a verified data chunk into a decentralized cluster. If the target node's internal clock has drifted away from network consensus, a conflict occurs. The node checks the timestamp against its local time and actively rejects the chunk. Cryptographic consensus mechanisms require precise, synchronized timeframes to validate operations and prevent spoofing across the network. A single rejected chunk is a minor delay, but when uploading a massive file requiring hundreds of validations, these clock errors compound into a total failure. Reaching true reliability means designing protocols robust enough to anticipate these hardware failures and gracefully route around them. The V version 0.6.7 update demonstrates that unmanaged hardware can reliably sustain high-velocity throughput at scale. This state resulted from three specific technical adjustments: a decoupled client architecture, tuned Catamelian routing, and the removal of odd-depth Merkle tree bugs. Multi-region testnet validation confirms these optimizations hold steady under the strain of over 900 active nodes. The ultimate goal is to make the underlying complexity of node configuration entirely invisible to the end user. Stabilizing the protocol for large file uploads is the final prerequisite for the network's next product phase. Once those final edge cases are closed, the reading room content will go live to the public. Closely following that rollout, the network will deploy the Indelible feature set. Achieving decentralized scale requires a completely frictionless foundation, one that is fully capable of supporting the next generation